Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to the subject digital image processing. This video is from chapter number 3. The chapter is titled Image Transforms. See, image transforms are having mathematical background, are very popular and having importance in the subject digital image processing, because as we see the digital image, it can be modeled as simply the array or a matrix, and whatever the operations onto the arrays and matrices are there, we can perform onto the images and we can obtain several kind of results to have different applications in this particular domain. So actually in this chapter we first of all reported with the topic, that is what is the need to have the image transforms, and started image transform one by one. So very first image transform, it was two-dimensional discrete Fourier transform. It followed two-dimensional discrete cosine transform. These both the transform switches us from the spatial domain to the frequency domain. So whatever the simpler tasks we see as multiplication into the frequency domain, these are very much complex into the spatial domain or time domain. Generally we see, like for example the convolution in the case of multiplication. So in the discrete Fourier transform, the representation is with the help of complex exponentials, complex coefficients we can say, and in the discrete cosine transform, the representation of the spatial domain data in the frequency domain is with the help of real coefficients. We have also gone through the introduction to Walsh transform, Hadamard transform, and lastly in the previous video the KL transform. So the applications of KL transform for clustering analysis, also for the image compression, is also addressed. For these many transforms, we have also tried to demonstrate the results onto the image samples with the help of MATLAB software. Now it's time to have introduction to the singular value decomposition and its significance into the digital image processing. So let us begin with the topic. So here we start with our topic, singular value decomposition, a popular tool in the family of image transform. The domain is digital image processing here. So to talk about singular value decomposition, we have the information that it is a very handy mathematical tool. That is why it is very much popular in this particular family of image transform. The invention of this singular value decomposition was originally for the square matrices, and it was independently discovered by the scientists. Names are here, the Beltrami in the year 1873 and the Jordan in the subsequent year 1874. But as of now we see the images are as the square grids or rectangular grids, so we should not be always confined to the square dimensions. So next, this particular singular value decomposition from the square matrices was extended to the rectangular matrices also by the scientist E. Clark and the Young in the year 1930s. So I hope after this extension, right, from the square matrices to that of the rectangular matrices, it is very much convenient to work on any dimension of image. Next, the singular value decomposition of a rectangular matrix. Suppose the matrix representation is with the help of capital letter A, is of the decomposition form. So now we are going to see exactly the formulation, how the decomposition in the terms of singular value for any matrix. First of all, matrix is our actually the signal here, image sample we can say, will be done in the form. So the formulation is simple. So capital A, the matrix image sample, so this is the input matrix that we need to provide here, and it will be decomposed into these three components or three matrices we can say. So the very first matrix is the left singular matrix we can say. This V transpose, V to the power T, is called as the right singular matrix, and this central one, that is the called as the singular value matrix. So U into W into transpose of V matrix. So whatever the input we have provided as matrix A, that is to be decomposed into three components, three matrices we can say. Now the question is, what is the significance to decompose into three parts? The significance is obvious that if the simple task of image compression you need to do, so that time you can have storage or transmission of the entire image sample in terms of these particular components. So let us have introduction to this brief formulation. A is equal to U into W into V transpose. So in the terms of matrices, we can have the representation like this also. So basically the U vector and V vector are having singular dimensions. We can say if this is the column vector, column matrix, I can say this is the row matrix, we can say, and generally the central one is having the elements into the diagonal orientation of that particular dimensions of the matrix, we can say. So this is the input data and that has been decomposed in the three ones. Now here U is having the dimensions m by n and it is orthonormal. W is of the n by n diagonal. V is also there, it is also orthonormal. So whatever the dimensions of matrix A, we can say m by n, that are decomposed into the three. So the orthogonality condition for the image transform, that is very essential, that is also here. So along with orthogonality, orthonormality is also followed by the vectors or the matrices, you can see V and U. So we can say that in the family of image transform, what we call the basis functions, so U and V along with this particular W acts as the basis vectors, basis matrices for the input sample, we can say. So this particular matrix W has coefficients and the diagonal coefficients here we represent with the help of W suffix I. So these are also called as actually called as the singular values of the input matrix A. The singular values actually appear in the descending order along the main diagonal of W that we have just now seen. So the singular values are actually obtained by taking the square root of the eigenvalues of A into A transpose and A transpose into A. Basically, if you talk about matrix, it is a collection. It is a collection of coefficients. Simply, if you are having certain kind of linear equations and the coefficients are to be collected, that can be represented with the help of matrix. So eigenvectors in terms of or with respect to those particular linear equations, we can say these are actually the roots. So the value that satisfies that particular criteria into that equation is called as a root, and here in terms of matrices we can call the eigenvalues, and further we have in the terms of eigenvectors also. So how to obtain these particular singular values to represent into the central matrix W? So that is by taking the square root of the eigenvalues of A, matrix A product with transpose of itself, and the transpose of A product with itself. Next, if A is singular, sum of the W suffix I coefficients will be equal to 0. So the condition of singularity for the matrix will be if it is positive, so that time some elements will be equal to 0. In general, for matrix we know that rank is a very significant information. So rank of any matrix A, the input matrix in our case, is actually the number of non-zero values of Wi. So W suffix I are the diagonally oriented values into the central matrix, that are the singular values, and how many number of non-zero values are there, that is actually the rank of the given input matrix A. So singular value decomposition, here we can abbreviate with SVD also. So it is mostly unique for any of the image sample, it is not common. So it is for the uniqueness, the limit is up to the permutation of singular values, or if some W suffix I are equal. Now the decomposition we have just now seen with the help of formulation A is equal to U into W into transpose of matrix V. So here U and V are calculated as the eigenvectors of A and A transpose and A, just now we have seen. So it is applicable to both of these particular matrices, and the square root of these eigenvalues are the singular values along the diagonal matrix D here. Sometimes this particular central matrix, what we have represented with the help of capital letter W, is also represented with the help of capital letter D, as it has diagonal elements only. So if the matrix A is real, then the singular values are always the real numbers, and U and R also the real. So the applications of SVD in image processing, if you need to address, so a summary can be made here, that the very first application, SVD approach can be used in image compression purpose. So to decompose a given image sample, we can have saving the memory space required to save the entire image. Next, SVD can be used in the cases of face recognition also. For any of the reference image sample, the components will be unique one. So for the applications like face recognition, uniqueness with a person is required, and hence the property of SVD as uniqueness, for uniqueness can be used for the application of face recognition, we can say. Next applications are SVD can also be used for the purpose of watermarking. SVD can also be used for the purpose of texture classification. Various types of textures are there into the images that we are going to go for details into the subsequent chapters definitely. So for SVD tool, this is also the application for watermarking and texture classification. Now we shall talk something about SVD and inverses. As we know that the singular value decomposition for input matrix is in the term of 3 matrices. So what are the advantages offered while working with the inverses of matrices that we see here? So this is the reason why SVD is so useful, that the results with the help of the inverses of these matrices. So this is application number 1, we can say. And here for the input matrix A, if we represent inverse, so it will be A to the power -1. So whatever the simple formulation you have earlier seen, that A is equal to U into W into V transpose, on taking the inverse, that will be modified to this particular form, the inverse of transpose of V, the inverse of W and inverse of U. So it shall finally give us V W inverse into U transpose. So now you see that these two components are just swapping their place. So here initially it was U, now here it is V, and in the place of third matrix as a transpose, it was initially V, now it has V here. So using the fact that inverse is equal to transpose of these orthogonal matrices, so in the case of inverse also the orthogonality is maintained. So since W is a diagonal matrix, the W inverse is also the diagonal with reciprocals of entries into the W. So for this particular central matrix, what is having the singular values in the diagonal elements, the necessary condition that except the diagonal elements, other elements are equal to 0. So on performing this particular operation, that is also maintained, the values are again into the diagonal elements only, just the reciprocals of the earlier entries, we can say. Next, A inverse, just now we have represented by this particular equation, VW inverse U transpose. So this condition actually fails when some W suffix I coefficient, the diagonal elements, are equal to 0, because as we are taking the reciprocals of the entries, the 0 will go into the denominator. So it is supposed to fail for the singular matrix. Now the case is also called as the pseudo inverse if Wi element is equal to 0. So this is 1 upon Wi, so 0. So that is the question here. So this is actually the closest matrix to the inverse. It is defined for all even non-square and singular matrices, and it is equal to A transpose A inverse A transpose if A transpose A is invertible. Now we have another comparison and more details with respect to SVD and the very popular technique into the image processing domain, that is PCA. SVD, just now we have seen that it is standing for the singular value decomposition. Principal component analysis is actually abbreviated as PCA. So as the name suggests, principal component analysis, whatever the information, now in our case the information is in the terms of image sample, two-dimensional information we see. So that particular information is stored in this particular technique in some principal components. Rest of the information part is not that much into another components. So a data redundancy is possible with the help of PCA. So PCA is also as like the SVD will be working for the image compression, data redundancy we can say. So let us have the information about the two. So PCA, just now what we pronounce principal component analysis, PCA. So it is actually approximating a high dimensional data set with lower dimensional subspace. So high dimensionality is reduced to lower dimensionality we can say. In the terms of geometry, you can see here whatever the data points are here available. So from these particular data points, as far as the axis are concerned, the variance as like into the KL transform what we have, so that particular is found and the components of principal values are obtained. So the first principal component will have some direction with respect to some axis. The second most will be having another direction, and these two directions are making orthogonality with each other. So that is a very basic condition for any of the image transform, that these individual components should be sometimes that much able to represent the image information or any kind of information provided in that particular technique. So this was PCA. The data matrix with the points as row take SVD. So here subtract out the mean, the whitening in case of image we can say. The matrix V that we have seen, so columns of this particular are actually the components. So this way we can relate SVD to the PCA. This is from the formulation of SVD what we have seen. The values of W suffix I gives the importance of each component. Now SVD approach is basically from the mathematics to sort out the data, to work out with the complex or wide data we can say. For example, if we are having a restaurant and we are having certain fixed customer, and these customers are ordering food of various types from this particular restaurant. So in the case if the restaurant wants the data as such that which particular customer likes which type of food, so that time that can be stored in the terms of three components, as like we have seen the formula A is equal to U into W into V transpose. So in these three components, so we can be storing what are the dishes available, what are the customers available, and what is the like of that particular customer. So this particular WI decides or stores the strength of that particular likeness. In terms of food we can say that if some customer is liking the spicy food, if some customer is not liking that particular spicy food, so those particular coefficients will reflect that particular information. So the strength of that particular information will be actually lying into these WI coefficients and are actually called as the singular values. Hence the technique is named singular value decomposition. So now it's time to talk about a simple example to work out with this particular technique. So here if the input matrix is represented by capital A, so it is having 1 2 3 4 rows and 4 columns. So total 16 coefficients values are there into the input matrix A, and if we apply the procedure of SVD, so we proceed further with the formulation of this A in terms of the three components shown this way also. The sigma suffix I here represent the singular values, so summation sign is here, so it is obviously the same representation as we have seen earlier. U and V are also there. So in terms of coefficients, ith coefficient out of 1 to n we can address here with the help of this particular formula. Now upon having the singular value decomposition, the first matrix what we call U, so for the given case of A matrix we can obtain it as a collection of U1 to UN, and here it will be this particular matrix. Next the V matrix V1 to Vn we can find out with this particular representation, and the third matrix that we earlier represented with W, that is also represented sometimes by capital D, as it is having the diagonal elements, can be represented like this. So here these are the singular values of this particular input matrix. So this input matrix A is now decomposed into three matrices U, V and T. We can have representation U into D into V transpose in this case. If we can take another example, the statement is like the find the singular value decomposition of this particular matrix. It is having 2 rows and 3 columns. So first row is having the elements 1, minus 2, 3. The second one is having 3, 2 and minus 1. So in this case, if we need to apply the singular value decomposition as like the previous example, what are the steps to be followed to have that particular representation? That we can have a summary here. So I can list out the steps. So very first step is conversion of a given rectangular matrix into the square matrix. See, in the earlier example, the rows were 4, the columns were also 4, so the dimension was of a square matrix. Now in this example, we have 2 rows and 3 columns, so it is a rectangular matrix. So though singular value decomposition is extended from the square matrices to that of the rectangular matrices, the very first step will be to get that converted into the square matrix. So in that case, it will be multiplied to its transpose. So 2 rows 3 column matrix will be multiplied to 3 rows 2 column matrix. So the resultant will be of square dimension, we can say. Next step will be to find the eigenvalues of the square matrix. So in the engineering mathematics, you know that how to find the eigenvalues. The formation of eigenvectors from the previous step, then normalization of this particular eigenvector. It will be followed by generation of the u vector, the v vector and the determining the d vector that holds these singular values. Lastly, reconstruction of the matrix A from the computed u, v and d vectors is also possible. So the inverse, what we exactly say, so it is also possible for the method singular value decomposition. So this was the method, and for the given matrix A, the 2 rows and 3 columns just now you have seen, so it can be worked with this formula. So instead of the matrix W or matrix D, it is also sometimes represented with the help of sigma sign. So u, v transpose and sigma that holds diagonal elements. So u vector is represented here. So it has 2 rows and 3 columns, 1 by root 2, 1 by root 2, 0, minus 1 by root 2, 1 by root 2, 0. The sigma will hold only the diagonal values, so it has the dimensions 3 by 3. So under root 18, under root 10 and 0 are the diagonal values. So in this case, w suffix I, what we see, so one of the value at this particular third row and third column is equal to 0. And the V transpose matrix is represented here minus 1 by 3, minus 2 by 3, 2 by 3 in the first row, 2 by under root 5, 0, 1 by under root 5, minus 2 by 3 under root 5, under root 5 by 3, 4 upon 3 under root 5. This forms the V transpose matrix. So if we have the product of these 3, so initially we have the product of the 2. The first 2 will give us under root 9, under root 5, 0, minus under root 9, under root 5, 0. It will be multiplied to the third matrix, and finally we obtain the input matrix 1, minus 2, 3, 3, 2, minus 1. So this was the input matrix to the singular value decomposition that we fed. We followed the procedure to have singular value decomposition. We obtained the 3 coefficient, and this way we can reconstruct the input matrix. So I hope you have understood what exactly the singular value decomposition is. Whatever the information we have discussed will be definitely helpful for you to work out for singular value decomposition and the reconstruction of the input matrix. So in the next lecture we are actually working with the same technique, singular value decomposition, with the help of MATLAB software. So we will be having a brief programming to show you the demonstration of this particular singular value decomposition. So if you like the contents and want to have some more details of this subject, digital image processing, you can subscribe to Ekeeda channel. Thank you.